We're now going to consider banked terms. So banked terms can be really confusing, but actually they're just using the physics that we've learnt about so far. So hopefully this will make it clear to you how we can put it together to answer these banked curve questions. So you've probably noticed banked curves before. If you're driving down a fast road and it turns a corner, then you may have noticed that the road tends to be banked at a small angle. And this is to stop you flying up the road out of control. So where you would have also seen this is in cycling, in Olympic events. When the cyclists go around the stadium is banked to stop the cyclists going up the slope in an uncontrolled way. So let's consider what angle should our road be banked at. So to keep it simple, and because it's sensible, let's consider the case initially with no friction. So if there is friction, then the angle can be a bit shallower than this. But if we want to be really careful and we're an engineer, say, we would want to design a road where even if it was icy and the friction really dropped away, cars would still be safe going around that corner at the recommended speed. So let's come up with an expression describing the angle at which the road should be banked. So banked curves look a bit like this. So let's take a curve with a radius of curvature of r, and we'll consider the curve which is banked at an angle theta here. So like we always do, we're going to start by drawing a free body diagram to describe the forces acting on our car as it transverses this curve. So because it's going around in a big circle, we know what the net force is on that car. It's described by our equations for circular motion. So we've got the centripetal force acting towards the center of the curve. So that is our resultant force. Okay, now considering the forces which are actually acting on the car, so remember there's forces acting which are causing this circular motion. So the forces acting on the car, we've got the weight force, which is pulling the car downwards, so that's a vertically downwards force. And then we've got the normal reaction force, which is perpendicular to the slope, to the inclined plane, or the banking in this case. So what we're going to do in this case is actually break our forces into components which are vertical and horizontal. The reason we're choosing this is that our resultant acceleration, we said, was horizontally towards the center because the car is transversing a circle, and so the net force is in the horizontal direction towards the center. Okay, so with our weight force, this is already a vertical force, so it's got 0 horizontal component, and the vertical force is just mg going downwards. Now our normal force, we can split this into a horizontal component towards the center of the circle, which is given by the normal force times sine theta, and a vertical component, which is given by the normal force times cos theta. Now what we're trying to do is to find theta. In the horizontal direction, the only force acting is the horizontal component of the normal force. So that must be equal to our net force in the horizontal direction, which is the centripetal force. So we can write that in the horizontal direction, the forces acting are n sine theta, and this is equal to the resultant force, which is mv squared on r. Now the problem is, at the moment, we don't know what that normal force is. But we can actually work that out by considering the forces which are acting vertically. Now, vertically, there is no net force because our car is not lifting up off the track or falling down into the track. So vertically, there's no net force. So the two forces acting upon it vertically must be equal and opposite. They must sum together to give 0. So vertically, we've got n cos theta going up and mg going down. So we know that n cos theta minus mg equals 0. So we can rearrange this and we end up with n is equal to mg divided by cos theta. So we now have an expression for n, and now we can substitute this back into our original horizontal equation. So replacing n with this new expression mg over cos theta, we've now got mv squared on r is equal to mg on cos theta times sine theta. Now sine theta divided by cos theta is just tan theta. So we have mv squared on r is equal to mg tan theta. We can divide both sides by m, and so rearranging this, we have tan theta is equal to v squared divided by r times g, and so theta is equal to the inverse tan of v squared over rg. So we've now come up with an expression for the angle that our curve should be banked at depending on the speed of the cars going around that turn. So depending on the speed limit, we can choose to bank our curve at different angles. And you'll notice that it doesn't depend on the mass of the car, which is great because it means that the same angle works for all cars and motorbikes and other road vehicles. Now it gets a little bit more complicated if we don't assume that friction is equal to 0. So let's have a look at a worked example now where we'll work out what speed a car can safely traverse a bend at if the friction is not 0.
Okay, so this example question is, what is the maximum speed a car of mass m can traverse a banked turn with a radius of curvature r at without moving up the inclined plane? The turn is banked at an angle theta. The coefficients of friction are μs and μk. Okay, so the best way to start this is by drawing a diagram. So let's draw our banked turn, and here's the car, and now we'll draw the forces acting on the car. So we've got our weight force acting downwards, so that's mg. Then we've got our normal force, n like that, and we've got the frictional force, and we don't want the car moving up the plane, so we can assume it's moving up the plane and the frictional force is opposing that. So the frictional force is here. Now what we're going to want to do, because this is a banked turn question, is split the forces into components which are vertical and horizontal. And we do that because we know that the resultant force is a horizontal force back towards the center of the radius of curvature. So let's start by splitting this normal force up. We can split it up this way, and if this angle in here is theta, then this angle here will be theta. One of the reasons we know that is that the angle here will be 90 minus theta, and then the angle between the normal and the plane is 90 degrees, so this angle here must be theta. Okay, so if that's theta, then this one here is equal to n cos theta, and this horizontal part is n sine theta. And similarly with the frictional force, we can split it up into a component which is horizontal and vertical. And if this is theta down here, then we can see that that angle there is going to be theta. Just these are alternate angles on parallel lines. And so this will be the frictional force times cos theta. And vertically, we've got the frictional force times sine theta. Okay, so we're going to start with the vertical components. Now the car is not moving up or down vertically, so we know that these forces must sum to 0. So the forces up, we've got the n cos theta. That's our only force up, and then we've got the frictional force and the weight force. So minus the frictional force times sine theta minus mg, and that is equal to 0. And now the frictional force is just equal to, in this case it's a car, so the wheels are rolling, so we've got static friction times the normal force. And so we've got, substituting this into the equation above, we've got n cos theta minus mu s n sine theta is equal to mg. And so we can rearrange this. We can pull n out as a common factor, and then we've got cos theta minus mu s sine theta, and that's equal to mg. So we can come up with an expression for the normal force. The normal force is equal to mg over cos theta minus mu s sine theta. Okay, now we need to consider what's happening horizontally. Now, horizontally, there is an acceleration because it's undergoing centripetal acceleration. So the resultant force is mv squared on r towards the center of the turn, i.e. left in this case. So the resultant is going in this direction, purple. Okay, so let's scroll up a little bit. Okay, so we can say mv squared on r, that's the resultant. Now we've got the frictional force, the horizontal component of that acting inwards, and the horizontal component of the normal force is also acting inwards. And so the frictional force, that's just mu s n cos theta plus n sine theta. Okay, let's pull n out as a common factor. Now what we can do is we can substitute in the expression we derive for the normal force from up here in here for this n. So we have mv squared on r is equal to mg over cos theta minus mu s sine theta times mu s cos theta plus sine theta. Now we've got an m on both sides, so they'll cancel out, and so we end up with v. And so we end up with v squared is equal to rg mu s cos theta plus sine theta over cos theta minus mu s sine theta. So to find v, we just have that v is equal to the square root of this expression here. So hopefully that made some sense to you. The trick here was to break all the forces into their components in the vertical and horizontal direction. And the reason we're using that trick is that the resultant force from the circular motion is in the horizontal direction.